Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today we are going to continue and finish what we started on MapReduce. Then we'll move on to Spark. But before we start, I have 3 questions for you. So this is the first one. What is P1DT7H2M3S? Is it a UTF-8-based encoding of the protocol buffer? Is it a string in the lexical space of daytime duration, which is an XML schema type, and also a JSON type? Or is it an instance of a Bison instance in base64, a binary encoding for JSON? Or is it the name of a new robot featured in the next Star Wars movie? We have a majority. And indeed, it is a lexical value or a literal, you can call them that way, which is basically a string set of characters, but it can be parsed to a daytime duration. And you might remember that all atomic types work like this. They have a value space with the actual mathematical values, and then there is a mapping to strings, which are lexical representations or literals. And this is the ISO 8601 standards that tells you that. So it's 1 day, 7 hours, 2 minutes, and 3 seconds. Okay. Then we have this question. This document is well-formed only, valid only, well-formed and valid, or neither of those? We have a majority. All right, and the majority is correct. Can anybody tell me why we cannot say that it is valid? Yes? We don't have a schema, exactly. So if you don't have a schema, then you cannot say anything about validity, because that only makes sense with a schema, right? But well-formed, that's fine. So remember that well-formed means you can parse it and turn it into a tree representation in memory. That's well-formed. Validation is the next step. With a schema, you can then annotate with more specific atomic types and type names, and you can also probably use a more efficient memory representation based on the types. All right, and question number 3. You have just submitted a typical MapReduce job onto a large cluster of 1,000 nodes. What do you do? It's done before you ask, you go check the results, or you go for a cup of coffee, it will be there when you are back, or you switch to something else and we'll check again in a few hours or tomorrow, or you hide from the CFO. Aha, we have a majority. Okay, so you like drinking coffee, right? Okay. But the answer is actually this one. It's not really just a matter of minutes. So typically when you use a cluster of machines, like 1,000 nodes, we are really talking about several hours, even overnight, maybe even more. There are even machine learning jobs that take weeks or even months. So the intuition here is really the 1,000 node cluster. If it were just a few nodes or just on your laptop, then yes, that can also take a few minutes. But you really have to imagine that if you use 1,000 nodes in the cluster, then first it means you have a lot of data that you need to process if you went through the trouble of taking 1,000 nodes. And the second consideration is that setting up all of these nodes and orchestrating the communication between them is not free. So it causes an overhead that adds to the whole thing. So it's definitely not just a couple of minutes. All right. But again, because I said 1,000 nodes, that's why. Okay. So that brings us to the slides. All right. So I left you with the fact that we basically have collections of key values. So basically, you know, when you have a hammer, then everything in the world looks like a nail, right? So to MapReduce, the input is a collection of key value pairs. The intermediate input is a collection of key value pairs, and the output is, guess what? A collection of key value pairs. So basically, whatever we feed in there has to be a collection of key value pair. But in the real world, it's not always a collection of key value pair. So we have, again, an impedance mismatch. We love this word in databases. So we need to figure out how to turn them to key value pairs. And I left you with this, with the idea that, for example, if you have a text file, then the lines of text are the way you tokenize. So you basically, at every new line, you cut it here and get a separate key value. And what you use here for the key is actually the offset. So it's the number of characters since the beginning of the text documents that precede the line, right? For whom does that make sense? For whom does that not make sense? Okay. Then we have other ways, right? So just to show you everything we have on the menu, you can also use the special characters of your choice, of course, to separate the key and the value. And then whatever is on the left, on every line on the left of that character gives you the key as a string, and whatever is on the right gives you the value. And then you basically turn this document into key value pairs. Right. This is actually very popular. For example, if you do meteorology, then typically this is the sort of things that you're going to have. But of course, it depends on the data set that you're considering. Obviously, this data set would just be text written by humans. This data set would have been prepared in such a way that it has this key value pair on every line. Right. Something else no, not something else actually, so these two. I want to give you an example based on this, on how we can use MapReduce to count the words. What I mean is we want to know for every word, how many times does it appear in the documents? Very much like the Pokemons actually, what we did with the Pokemons. So how do we do it? Actually, can you try to guess the map function and the reduce function that I can use for that? What map function and reduce function would give me as the final output key values where the keys would be the distinct words and the values would be the counts. Any idea? Yes?
On map a string of words to like every word being key and the number counting the value.
Yes. Yeah, so I'm repeating in the microphone so that everybody hears. So you basically suggested to have as a map function basically a tokenizing function, right? You tokenize, for example, based on spaces or punctuation, the words. And then for every word, you create a key value pair. The key is the word. And you suggested what would be the value for every word? Already the count per line, right? Okay. So that's very interesting because you're already one step further. We'll look at it later with the combine function. In fact, for now, we can keep it simple and just say that every word gives you a value of 1. And if you have multiple occurrences on the same word on the same line, you just repeat it with a value of 1, right? For now, but I'll come back to it because for the Pokemons, you actually already also directly put the local count. All right, so this is my suggestion, right? So the basically based on yours, but just changing the value to 1. So lorem 1, ipsum 1, $1, and so on, right? But by the way, you know, these words here, these are the, in the publishing industry, you probably already saw them. It's just some standard thing you use when you want a placeholder. So it doesn't really mean much, but this is commonly done. All right, so then the reducing function, did you also specify it or just a mapping function?
Mapping function would just be a summation of all.
Yep, so you sum, exactly. So that's the reducing function would sum over all these ones and find 7. Technically, because I have only ones here, you could count or you could do the sum. It's the same thing, right? So let's say the sum. So we get 7. So that's our first MapReduce job, actually. So you see, with MapReduce, you can count the number of distinct words and the number of occurrences in the documents, right? For those of you who are in information retrieval, you see how that fits, right? In the bag of words model, that's how you could build vectors, for example, of term frequencies. All right. Another one. So now what I would like to do is take these lines of text, and I would basically want to do a grep. You know grep, right? This is how you test if a line contains something specific. So a filtering query. What map and reduce functions would you use for that? Assume I'm giving you a predicate. So the predicate takes a line and tells you yes or no. Based on that predicate, what would be the map function and the reduce function? Yes? Maybe the microphone so that then I don't need to repeat.
So the map function would just either return no line if the predicate is not true, and would return the line if the predicate is true. And then for the reduced, you could either use the identity, or maybe you could combine it back into one document, for example, if you so desire.
Yeah, absolutely. So for the map function, indeed, either you pass over the line unchanged or you don't. And for the reduce function, the identity is perfect, right? So this is indeed it. So this is the map function. So visually, imagine that the predicate says yes for the first and fourth one and no for the second and third one. So you basically, in that case, the intermediate key values are a subset of the input key values, right? We just filtered. But then we're pretty much done. So the reduce function is just the identity, right? In fact, it's pretty common to have an identity reduce function. You can even have in MapReduce some check that says there's no reduce, like it's just directly the input of the mapping phase. All right. For whom is that clear that it works like this? All right. In fact, what we've just implemented is a selection in the relational algebra, and that's basically the where clause in SQL. Right. I'm just saying that for future reference, but this is in essence something we can do with MapReduce. Since we're at it and I said selection, the little sibling on selection is projection. How can we project? Can you tell me the map function and the reduce function? So I'm assuming here that my input is not just any text. Let's say it's JSON, right? I have JSON lines. And every value is going to be a JSON object, right? And technically, it's a string. So for MapReduce, it's just a string. But what is your map function and your reduce function for projecting to less columns? Yes, over there.
In the map function, we first parse the string to JSON because MapReduce does not understand JSON. And then we just select the columns or the entries that we're interested in and encode it back into a string and output it. And then as before, we can just use the identity for the reduce function.
Yep. What is the verb for encoding back? Do you have a more precise verb? The opposite of parse? Starts with an S. Anybody? C, yes? Serialize, exactly. And you're exactly correct. This is exactly it. So indeed, MapReduce doesn't understand JSON. So you parse the string into a JSON object. For example, if you're using Python, that would be a dict. Then you use the API of the JSON library that you're using, could be anything, and then you project to the columns you want. And then you serialize it back to a string, and that's your intermediate key values. All right. So you see here, there's a bit of an overhead with dealing with JSON because it doesn't understand JSON, but I'll come back to that, right? Okay. So that's basically what you've just said. The map function and the reduce function is just the identity, right? In fact, when the reduce function is the identity, that's kind of nice, right? Because there's no shuffling. And so that basically means that projection and selection are not very costly, right, in terms of cluster use, right, because we don't have to shuffle anything, right? That I'll come back to in the lecture on Spark. Very good. So we had 3 examples: how to count occurrences of words, how to select, and how to project. So we already have the select clause and the where clause of SQL, right? So that's a pretty good start. All right. Now, I would like to come back to what you said earlier about directly outputting the number of words in the line rather than having a key value for every word with a 1, right? In fact, that is an optimization. And you're absolutely right that it works as well. So the idea is that generally you would have these 2 phases. So you basically have the map phase over there and then followed by the reduce phase. But in basically the problem is the shuffling, right? It's the quantity that you shuffle here, and you want to keep that quantity to a minimum. You would like to not completely overheat the network cables, right? So this is a common thing that we try to do in database systems, especially when we work with large amounts of data. We try to find all kinds of tricks and optimization to have less data in memory, less data over the network cables, and so on. So less bits. So there is indeed a way to have a lesser amount of data in the intermediate stage. Sometimes, not always. And in fact, that is called a combine function, right? So the idea is that it's also the user who has to specify that. So there's the map function, the reduce function, and the combine function. It has to be supplied by the user. And basically, the user would just additionally specify a combine function. And what it means with the combine function is that when the map slots process and create these intermediate key values, they can additionally use the combine function in order to have less key values. So a combine function takes several intermediate key values and outputs less intermediate key values, right? And hopefully the combine function has to be carefully chosen in such a way that it doesn't change the results, right? So when do you use the combine function? So I said the map slot can use the combine function. I didn't say it has to. You have no guarantee. You can specify a combine function, then MapReduce does whatever it wants. Maybe it will completely ignore it and not even use it. Maybe it will use it a little bit. Maybe it will use it a lot of times. You have no control over that. This is exactly why you need to choose wisely this combine function so that it doesn't matter. But basically, you remember that whenever the memory is full, we flush to disk or we compact and so on. So these are good moments to use the combine function, right? So that would basically diminish the size of the files that you would create on disk or even when you compact, right? Now, the combine function, that might sound tricky, like to find a good combine function. In fact, there are many cases in which it's not tricky at all because you can just use the reduce function also as the combine function under specific conditions. And these conditions are, and here I am taking my hand wavy thing because mathematicians are going to complain, but basically it has to be, it's sufficient for it to be commutative and associative, right? If you are using a reduce function that is commutative and associative, then you can use it as the combine function. And an example of that, I have an example here. Yes, here. So basically, if I'm counting the words and the number of occurrences of unique words, then my reduce function is plus, right? It's the sum, 1 + 1 + 1 + 1. So it's plus. Plus is associative and commutative, right? So because of that, I can use, if my reduce function is a sum, I can also use it as a combine function. You agree that plus is associative and commutative, right? This is the reason why it's totally fine if early on during the map phase, I already start summing up the numbers in here and it will not change the final results, right? So this is the trick. And now you understand that when I say associative and commutative, I don't mean the reduce function itself. I mean the plus, like the operator inside the reduce function should be associative and commutative if you use such a binary operator. Okay, for whom is that clear? All right, very good. So again, I repeat, you can reuse the reduce function also as a combine function. You need for that, for the key types and the value types, the intermediate ones, to be the same ones as the output key value types and of the output of the reducer. Because the combine function can be called any number of times. You can call it even 10 times on the same data. So it has to preserve the types of the keys and of the value. And then it should be commutative and associative, again, with that little asterisk. If you literally look at the mathematical definition of the reduce function, you will see you cannot say it's commutative and associative, but this is just the intuition I'm giving you. Technically, very often you define the reduce function as taking key value pairs, keeping the key, and just applying a binary operator to aggregate the values together. If that operator that you apply is associative and commutative, then you can use as a combined function too. All right. And so the idea here, where it's brilliant, is that this combining of early, trying to apply the sum very early as possible, is again this idea of bringing the query to the data. You want to do the computations as early as possible, especially if the computations diminish the amount of data. If computations diminish the amount of data, the earlier you do them, the less data you will have that has to flow over the network. For whom is that clear? All right. There is a generic term for that I'll come back to. It's called push down. When you have some computations, you try to push them down so that they are executed as early as possible to use less network, less bandwidth, less memory, less disk. Okay, so that was my example. Plus is commutative and associative, so I can use that as combined. And again, I repeat, the way that this is done right here, using the combined function, you have no control over this, absolutely no control. MapReduce does whatever it wants. It could not use it at all, it could use it a little bit, so you have absolutely no control over that. All right, so now I will move over to the APIs. So it's implemented in Java, the native language of the MapReduce implementation, but you can also use it with Python and other languages. It's called MapReduce streaming. So that's basically, it can be used in conjunction with the standard input and the standard output on the command line. So basically your map function and reduce functions are bash scripts that basically take input and spit out something. And then that can be used as a very convenient means of using MapReduce. But let me focus on Java just to show you. You don't need to know Java, right? That's really not important, just so that you feel how it works. So basically, you need to specify a map function, a reduce function, and optionally a combined function. So that would be the map function, right? It takes a key, takes a value, and some context, and then it basically generates key values in there and writes them back to the context, right? So that's my map function. Again, it can generate 0, 1, or more intermediate key values, and that you can see with the number of calls to the write function. Every time you call the context write function, you spit out an intermediate key value. In that case, it's just 1. Then you have the reduce function. Look at the signature. The reduce function takes 1 key because it's a group of key values with the same key. So it takes 1 key, and then it takes all the values that are associated with this key, right? So this is the idea. And what happens is that you do whatever you want to do, right? And at some point you can call again context write with keys and values exactly in the same way as in the map function. And again, that can be 0, 1, or more times. It doesn't matter. And again, very often, the new key that you have here is in fact going to be the same key as right here, right? And the value might be a plus or whatever operator you apply to aggregate the values. But it doesn't have to be because you have a programming language, it's Turing complete, you can write whatever code you want in there, okay? So this is then, when you create your job, what it looks like. You basically give it a name. Then you say, this is my map function, this is my reduce function. So you do that using classes in Java. And then you specify the input path and the output path of the job. So where's the input data, where's the output data, possibly the format. So in that case, I think it's probably standard in that case that it's just text. And then you wait until it completes. Okay? For whom is that clear? All right, again, you don't need to know Java. That's just to give you a feeling of what it's going to look like. So it works with Java, with Python, with many languages. And finally, if you want to add a combiner, just say set combiner class. And of course, if reduce checks the reduce function checks the boxes for commutative, associative, and send times, you can just say set combiner class with the same class, my own reducer, right? So you just reuse it. But of course, the most general way could be any reduce function, any combined function. You can also write it as a different class. All right. Now, I would like to draw your attention to this mapper, combiner, and set reducer. If you look up literature on the internet or in books, you will hear a lot of people that talk about mappers and reducers and combiners, like mappers do this, mappers do that, and so on. What I would like to tell you now is try to avoid using these terms except for the names of Java classes. That's pretty much the only thing you can do. But avoid, when you speak and explain MapReduce, do not use the words mapper, reducer, combiner. Avoid that. I'm going to give you better words, and you will see that using these better words will also make it easier for you to understand what's going on, because it forces you to think clearly. And you will see then that mapper, reducer, and combiner are in fact ambiguous, because you're not precise of what you are talking about. So do not use these words. When you find them in books, try to map them to the words I'm going to now give you. And in order to explain that, I'm going to use an analogy. We have people who went together on a vacation, and they are about to write the postcards to all of their friends. So they have, in that case, 50 postcards to write. But there are several of them, so they are going to just sit around the table and start, because they know about MapReduce, so they are going to parallelize the whole thing. So the idea is that the postcards will be split into 5 heaps of each 10 postcards. I call them splits, right? A split is the pile of postcards. So there's a first split with a pile of 10 postcards, a second split with a pile of 10 postcards, and so on. That's a split. Next, we have the notion of a task. A task is a to-do. The task, number 1, is to write some text to your friends on postcards 1 to 10. This is a task. That's something you have to do, as opposed to the splits. This is the physical postcards, the splits. Who understands the difference between task and split? All right. So the task number 1 is to write some text and the addresses and so on postcards 1 to 10. Maybe put a stamp also. Then you have task number 2, the same thing on the second split, and so on. All right. Task. Remember that word. So they are sitting around the table, and what they do, there's 3 groups of people. We'll call them map slots. So they take, there's 3 of them, so they take the first 3 tasks, and task 4 and 5 can wait, they will be on later, and then they start writing the postcards. Now, there is a little bit of help in group number 2, so they are finished a bit earlier, so task 2 is done. What happens is that they grab the next task, task number 4, and just continue while the other ones continue on tasks 1 and 3. Right? Then group number 3 is done, so they take task number 5, and then complete. Now they're all done. Now you notice something, the number of slots is not the same as the number of tasks. We have 5 tasks, we have 3 slots. You also notice that this is happening dynamically. It means that there is no static assignments of tasks to slots, it's just whoever finishes takes the next task. So you cannot predict in advance what's going to happen. For whom is that clear? Very good. So what happens now if I give you all the terminology? What we call map function is a mathematical function that takes 1 key value pair, 1 input key value pair, and outputs 0, 1, or more intermediate key value pairs. That's the map function. The reduce function is a mathematical function, possibly implemented in Java or Python, that takes a group of key values that all have the same key, and that should be complete. It should be all of the intermediate key values that have the same key, and output 0, 1, or more output key values. The combine function is a mathematical function that takes as input 1 or more intermediate key values, and spits out 0, 1, or more intermediate key values. Okay, that's the combine function. Then we have the notion of map task. A map task is basically, you can see it as the task of iteratively calling the map function over each key value. So it means you basically have a split that contains multiple key values. And you take each key value, and on each one of them, you call the map function. What is very important is that this is sequential. there is no parallelism in there, right? It's like the postcards. You have a group, you take the postcards, the 10 postcards on your pile, you do them one by one. You don't write all of them at the same time, right? So it's sequential. So first, the first key value, we call the map function, then we call the map function a second key value, and so on. You can see it as a thread, right? It's a computer program thread that sequentially calls the map function. That is the map task that does that, okay? Then we have the reduce task, which is also an iterated and sequential sequence of calls of the reduce function group by group, right? So each group of intermediate key values with the same key, we call the reduce function. This is again sequential, there is no parallelism in there. For whom is that clear? Right? So again, it's a thread that does that. Combine task, that doesn't exist. You will not find that anywhere because remember, the combine is just a function that can be used during the map phase to compress the data. So that's a function that you can use whenever you want to compress a little bit in memory or you flush or you compact. You use the combine function to reduce the quantity of intermediate key values. There is no such thing as a combine task. That just doesn't exist, right? For whom is that clear? All right, very good. Now, that's basically the visual. So the combine function is just used in order to have less intermediate key values by compressing them into less. Okay? Now, a map slot. You should think of a map slot as a CPU core. A CPU core is able to take on a sequential execution. Of course, with an operating system, you can still have threads and you know with scheduling and so on. But technically, one CPU core can do only one thing at the same time, right? So one CPU core gives you one slot, and what that CPU core is going to do is take one task, which is a sequential call of the map function. When it's done, it takes a new task from the tasks that remain. Again, sequentially calls the map function. Then when it's done, takes task number 3 and so on. So it means that it's sequential within a task, but it's also sequential across the tasks in the same slots. For whom does that make sense? Right, we have a question on Zoom, I think.
Yes, do we view the combine function as part of the map task?
I would say that it's really an implementation detail. It's really basically the MapReduce implementation of the map phase can just add arbitrary calls of the combine function. You could consider that it's part of the map task if you do it already while it's still not done, right? So if you call the combine function and do it on the fly. But I could also imagine that a combine function could be called after the map task, or for example, if the memory is full because you have too many map tasks and then you flush the output of previous map tasks to disk, then you could still use the combine function outside of a map task, right? Thinking out loud. Does it make sense?
Yes.
All right. So basically, MapReduce is free to do whatever it wants. It's free to call the combine function any times it wants to aggregate intermediate key values. All right. Now, one more thing about when I said CPU core, what I really mean is virtual core, because you might have heard of hyper-threading, right? It's a way that you can squeeze even more threads on the core. So typically, it multiplies the number of cores by 2. So you really already have to think of the virtual cores, right? So this is really whatever is the smallest unit when you can not parallelize within it, right? Okay, but then it doesn't seem very interesting because there's no parallelism, right? I just said everything is absolutely sequential in there. So for now, we don't have any parallelism. The same goes for a reduce slot, which is again a virtual CPU core that sequentially takes care of reduce tasks one after the other. Everything sequential. There is no combined slot that doesn't exist. You will not find any CPU core that is used in order to call the combine function iteratively. That doesn't exist. Then it starts to be interesting because if I talk about the map phase in its entirety, then I have several CPU cores, possibly even on several machines. And each CPU core, virtual core, is basically, I don't know what's going on with the screen now, it's the light or something. I'm still trying to adjust. I'll find it out. So with the progress of AI and the new Zoom update, it seems that we don't need the green screen anymore, but I still need to figure out exactly how the lighting should work. All right, so for each virtual core here, we have a slot, and every slot executes a sequence of tasks. For whom does that make sense? Right? And this is where the parallelism is, because the tasks get spread over multiple slots, and the slots are able to work in parallel. Okay, and the same goes for the reduce slots. Now, somebody asked last time about how many tasks should there be per map slot, and how many reduce tasks should there be per reduce slot. For map tasks, you basically need a multiple of the number of map slots. For example, I don't know, I'm just waving my hands, like 5 times more tasks than slots, 10 times more tasks than slots. These are good numbers, right? Basically, it spreads over the tasks over the cluster, even if some slots are faster than other slots. Then the faster slots will have more tasks, and the slower slots will have less tasks. For the reduced slots, there are 2 numbers that circulate over the internet, and these numbers are 0.95 and 1.75. So let me explain why these 2 numbers. So 0.95 basically means that if you have, for every reduced slot, you have 0.95 reduced tasks. What that means is you need to think of it with many slots. Imagine you have 100 reduced slots, then you should have 95 reduced tasks, right? So that's a way of not of having the cluster not fully busy in case something goes wrong somewhere. So this is the 0.95. Then every slot will have 1 task, and that's it. 1.75 means that you have 100 slots and you have 175 reduced tasks. It means that at first you take a bit more than half of the available tasks and do them in parallel. And then some of the slots that will be done faster will take on the remaining 75. And if there's a few that take longer, then that's okay. It spreads, it balances the load a little bit. So this is why you see the 0.95 and 1.75. These are rules of thumbs in order to configure that. All of that can be configured, by the way, in the configuration of MapReduce. All right, but I'll come back to this a bit later on optimization. Combined phase doesn't exist. There's just a map phase and a reduce phase with shuffling in the middle. Right, so this is how it fits. We have slots that process tasks sequentially, and they pick them dynamically. When they're done, they take another task. And a task is a sequential series of function calls, just like a slot sequentially executes tasks. What's more, in version 1 of MapReduce, the allocation of slots to map or reduce is static. So you decide in advance, every virtual core is either map or reduce, right? We'll fix that later, because of course it means that during the map phase, all the virtual cores that are supposed to reduce do nothing. So you're not utilizing the resources of your cluster fully. Okay. And finally, I would like to finish with a tricky point, but in fact, some of you already realized that, because I got that question, I think at the break last week, and that's actually an excellent point that you actually were able to find it by yourself. We basically have the tasks that correspond to splits, right? So the idea is that the sequential call of the map function here corresponds to the splits. So the splits are basically the HDFS blocks, if you want to see it this way. So a split is a block. But the problem with that is that splits and blocks are not defined in the same way, because you might recollect that an HDFS block is defined as a number of bits, 128 megabytes, and then it stops. You don't care what the data is, you just stop exactly after 128 megabytes. But the split is a set of key values. So now you see the problem. What's going to happen in reality is that when you have the splits, so a record, basically a key value pair in a split is somewhere in a block. But what's going to happen is that the very last record or the very first record of a split is actually going to be spread over 2 blocks. It's going to start at the end of a block and it's going to end at the start of another HDFS block. Who sees that? Right. That's really because HDFS blocks only see bits, right? That is a small impedance mismatch. It happens all the time, but that's no big deal. You just need to remember whenever MapReduce processes a split, that whenever it's done with a block, it has to also read the next few bits to finish the last key value from another block, right? And that's totally fine. But this is handled. This has to be done explicitly by the MapReduce code, not by the user, of course. If you're the user, you don't need to care about that. But the implementer of the MapReduce needed to be careful about that, right? Okay, so you need to finish with a remote read, right? And that happens actually if you look at the probability that happens. In fact, when it does not happen, it's really rare. Like when you have a key value that exactly ends at the end of an HDFS block, you really need to be lucky, right? Perhaps not as lucky as winning the Euro Millions, but still that doesn't happen very, very often, right? So this is really something you need to consider. And that is my last slide for MapReduce. We have a question?
So you said the last, if you read the start of the next block, that's a remote read. I don't quite understand why has to be a remote read. Could you just elaborate on that?
Yes, you're absolutely right. It could also be on the same machine.
Ah, okay.
Yeah, you don't know, right? It could be on the same machine. If it's on the same machine, you just can read it locally. And if it's on another machine, then you can just, you should have it over the network.
But wouldn't we expect it to probably be on the same machine?
That is a good question. So what is for sure the case is that when you know that, oh, well, it's getting even worse with the light, maybe it's the opposite. So basically, when you assign the next task, when a slot requests the next task, it's going to try to find the task that corresponds to data that there is on the same drive. That would be the most of the block. But in order to also make sure that the next block would also be on the same machine, that might not always be the case. I do not know to what extent they also try to anticipate when retrieving the task that also the next block would be on the same machine. That I don't know. It could be the case that they try to do a little bit something in that direction, but I'm not sure.
Thank you.
Thank you. Any other questions?
So the next node, how does it know how many bits from the beginning it has to ignore?
You don't know. So it's basically really down in the physical implementation details of MapReduce that there's Java classes that are basically responsible for taking care of this. And that I don't know the exact details of how far it goes, but basically. You basically cannot know in advance. If you haven't read the block, you can not know what there is in there. But I could imagine that there could be some optimizations that give you extra information on the limits of the splits, right? But here it goes beyond my knowledge, I would say.
I mean, the data is split without caring much about saying anything about how many of the first bits the next block is from the previous key value.
So if I think out loud, I would imagine that typically when you use MapReduce, you have some knowledge on like there's some homogeneity in the key values in some sense. But I'm really afraid of misleading you or giving you an answer that doesn't make sense. So maybe we could take this as something to investigate offline if we manage to find some more things regarding this. But you're bringing me outside of my limits, my knowledge here. Okay, which is good. I mean, it means that that's the goal of any teacher, is to bring the students all the way to the frontier. Yes.
And isn't it a problem that basically for every single block or almost every single block we have to do a network read because the last key value pair is going to be mismatched?
Yes, it is a bit problematic. Of course, our wish list, if we could have wished for something, that would be that it ends exactly at the end of a block, right? And then that would have been easier. So it is really something non-trivial that was, I would call it an engineering challenge. And that engineering challenge was part of the design of MapReduce to getting this right. What I want to show you here is it's not trivial, basically. Right? Okay, actually the break is perfect because now we can have the break right in the middle of the two. And after the break, I will start on Spark, right? So see you in 15 minutes.